And we'll get started. So, hello everyone. Thank you all for being here today. Today I'll be talking about efficiency and computational complexity, which is something that we've kind of touched upon a couple of times in this class, but we haven't really gone in depth, right? The focus of this class is really to teach you how to code and to teach you these different coding concepts. And we always say it doesn't really matter if your code is efficient or not. It doesn't really matter if you solve a problem using 5 for loops when you could be doing it just with a simple max, right? But when you go into the real world and you are actually coding for a project that you may have, you'll see that a lot of times we're working with inputs that are very large, right? When we're parsing through a text file, usually it's not just a text file with 5 lines. It's a text file with 10,000 lines. And if you can make your code more efficient, then you can make a lot better use of your time and the computational resources that you have. Because especially as you scale up to like the massive scale that these different tech companies, for example, or research labs are going to use, these computational resources get very expensive as well. So if you can know about computational complexity and know how to make these problems a little bit easier to solve based on the algorithm that you choose to use to solve them, then you'll be doing yourself and whatever company you work for a big favor. So first, let's start talking about what actually is computational complexity and how do we define it. So computational complexity is defined as the amount of resources that are required to run an algorithm. So it's how much energy, really, you have to put in order to run this algorithm. Now, there are 2 types of computational complexity, time complexity and space complexity. We are really going to be focusing on the first one over here today, because that's the one that's a little bit easier to understand and easier to explain complexity through. But space complexity is basically how much memory your algorithm is going to need in order to actually run, right? How much space it's going to need to store any like intermediate steps of the process or the final product. Whereas time complexity, as the name suggests, is how much time your algorithm is going to take to run based on the inputs that you give it. Now, these are both not absolute measures. So the study of computational complexity is not going to be able to tell you, oh, this algorithm is going to take 5 minutes to run, or this one's going to take 30 seconds, or it's going to be running for 3 days. What it tells you is how the complexity of your algorithm or how the time it's going to take to run or the space it requires changes as you change the size of the input that you pass into this algorithm. So, for example, the problem you might be trying to solve is you're trying to sort a vector, right? This study isn't really going to tell you how much time it's going to take to sort a vector. But what it can tell you is, say you have a vector of 5 elements that you want to sort, then you have another vector that's 35 elements that you want to sort. Is sorting the vector that's 35 elements going to take 7 times longer to do than the vector that's 5 elements long? Because the vector itself is 7 times longer? Or is it going to take 7 squared, 49 times longer to sort that vector? Or is it going to take 2 to the 7th, 128 times longer to sort that vector? That's what computational complexity tells us. So it really measures it as a function of input size. It does not deal in absolutes. It doesn't give you a measure in seconds. It just gives you an idea of all this. Now, how do we actually talk about computational complexity and study it? Well, in order to understand that, we need to understand what big O notation is. So big O notation is basically a way of telling us mathematically how the amount of resources that's required to run an algorithm or to solve a problem grows as you increase the size of the input to that algorithm. The notation for that is going to be something like this. So we have an O, right, just a big O, and then in parentheses we're going to have some function of n. And that function of n is going to be what tells us how these resources change with that input size. So if an algorithm has a complexity that is O of n, then that means that if your input size scales by a factor of n, then the amount of energy that it's going to take to run this algorithm is also going to scale by a factor of n. So that's that issue. If you have something that's 5 elements long and then you double it, it will take double the time to run this algorithm, right? Whereas if it's n squared, then when you scale the size of an input by a factor of n, then the amount of time it's going to take is going to scale by the square of n. So if you have a vector that's 5 elements long, and you increase it to 10 elements long, the time that it's going to take to run gets increased by a factor of 4, because you doubled the size, 2 squared, 4. And you can see that there's a bunch of different time complexities that you can have. Something that's O of 1, that means that the amount of time it takes to solve this problem or to run this algorithm is constant. You could give it a vector that's 1 element long or a vector that's 1,000,000 elements long. It'll take the same amount of time to do it. And very few actual real-life algorithms are O of 1. That's, if you can find an O of 1 algorithm to do something, then you're very lucky, because most of them are around the middle over here towards this end, which are pretty bad algorithms, right? So you can see that it falls sort of on this spectrum of more efficient to less efficient. O of 1, of course, is the most efficient. Then you've got O of n log n squared, 2 to the n factorial, n to the n, and it goes on. There's worse algorithms than that as well. And what we want to do is we want to find the algorithm that minimizes this big O, right? Because then that tells us that we can solve this problem using fewer resources. So just a quick visualization of what this actually looks like. So over here on the x-axis, we have input size. And on the y-axis, we have sort of the relative complexity based on that input size. So notice how a problem that an algorithm that's O of n, complexity just increases linearly with the input size. N log n, okay, it increases a lot more. N squared, 2 to the n factorial. So notice if you can find an algorithm that is O of n to replace an algorithm that you had earlier that was O of n factorial, you've just saved yourself orders of magnitude in terms of time for running this algorithm and solving this problem. So I really want to be looking at algorithms that grow like that versus ones that grow like that. Does this all make sense? Is this clear? Cool. All right. So this is the main idea behind big O. Now, when we actually deal with big O notation, there's a couple of different quirks in this notation that we need to look into because of this fact that we're talking about how this complexity scales with a certain number. So because of the way computers are right now, and just because of how fast and how powerful they are, solving a vector that's 5 elements long versus a vector that's 10 elements long is going to be instant. It's going to be pretty much instantaneous because computers are just so fast. They can do that. So even if you have an algorithm that isn't so good in terms of big O, when you give it small inputs, that's not really going to matter. We only really care about big O when we talk about massive inputs. So if we're talking about a vector that's 5 elements long versus a vector that's 5 trillion elements long, well then 5 squared versus 5 trillion squared is a massive difference, right? So we only care about big O when we talk about this input size tending towards infinity, which means that we really only need to consider this highest complexity term, and we can ignore these other terms that are lower complexity in an algorithm. So say we had an algorithm that that loops through a vector, right? And if the vector is 5 elements long, then it loops through that vector 25 times, right? That would be an O of n squared, right? But if we had an algorithm that's, for example, O of 2n squared, because it has to do that twice, when we take these inputs up to infinity, just multiplying infinity by 2, you get infinity as well, right? So we can just ignore these constants in front of our terms in big O notation, because as we scale our input, those constants aren't really going to matter. So we can treat something like O of 2n squared as just O of n squared. Additionally, if we have an algorithm that has multiple steps, right? And the first step of that algorithm is O of n squared, meaning the amount of energy it takes scales with the square of the input size. But then we have another step in this algorithm that's just O of n. And then finally, we have a step at the end of the algorithm that's constant, right? If we were to look at all of these different steps, truly the efficiency of this algorithm scales with n squared plus n plus 1, right? Because each of these steps has a different efficiency. But once again, because we're talking about bringing that input size up to almost infinity when we talk about big O, then this factor of n squared is going to be almost infinitely larger than n as we scale that input size. So we can almost ignore these terms over here, like 1 and like n, because the n squared term is just going to grow so much more, and it's going to be just immensely larger. So we can reduce that as well to just O of n squared. We can just ignore these other terms that are lower order. And then as well, if we have a situation like this, where we have O of n times log base 3 of n plus 2n. Well, n log n, it grows faster than n, so that means we can just ignore this 2n right here, because this is the higher order term. And we can also ignore the base of that logarithm, because you may remember from math class, right? If we have something like log base 3 of n, this is the same as log base 10 of n over log base 10 of 3, right? So this is the same as just changing it to whatever other base we want and multiplying or dividing by a constant. Because we said we can get rid of constants, that goes away, and all we have to say is n log n. We don't even care about the base of that logarithm. All that matters is that it's logarithmic growth. It doesn't really matter what base, because the bases are just changing it by a constant, right? So these are a couple of the caveats that you need to know when you're working with big O notation. By the end, when you're looking at an algorithm and you want to determine the final complexity of the algorithm, it's always going to be O of just a single thing. It can never be O of something plus something plus something. It's always just going to be a single thing, and that's going to be that highest order term, like we have over here, the highest complexity term. Did this all make sense? Any questions about this? Cool. All right. So now let's go through an example of a function that we have right here, or just a script, right? And we want to determine what the efficiency of this algorithm is going to be. So we can assume in here that n is just a vector and r is just a random array, right? And that n is going to have a certain length. We don't know what that length is, right? But we can consider that length to be our n in our big O notation. That's our input size, right? And we want to see, how does the work required to run this algorithm scale when we increase this n over here? So let's actually trace through what this algorithm is doing. So it goes for I equals 1 to the length of n. So we know it's going to have to loop through the entire length of n at least once. That tells us, just off the bat, that this algorithm is at least O of n. Because we have to go through each element of the vector at least once. That's what that outer for loop is telling us, right? If our vector is 5 elements long, we're going to have to loop through at least 5 elements, right? If it's 10 elements long, we'll have to loop through at least 10 elements. So it's at least O of n. We can get that from just seeing that there's a for loop in there that depends on the length of n. Now let's go on down here. We say s equals 1. Just assigning a variable, that's a constant operation. Just assigning a value to a variable, it doesn't matter how many times we have to do it. That's just a constant operation. So we don't need to care about that. Now here, we've got another for loop inside of that. So we're saying for j equals 1 to the length of n, again, that gets done every time that outer loop is run. This inner loop has to loop through the vector one more time for each time that the outer loop is going. So that immediately increases our complexity over here to O of n squared. Because every time that we're looping through this vector, we have to loop through it again. Right? So that makes this O of n squared because we have that nested loop in here. And now all that it's doing, it's saying s equals s times n of j, right? It's just accessing and doing multiplications, which is all we consider constant in time. And then it's just assigning that value to some index of that array. So the time complexity of this upper block over here with these two nested for loops is going to be O of n squared, because again, we're having to loop through this vector, and every time that we go through this vector, we loop through it again. So for each iteration, we loop through it one more time. That makes that O of n squared. And then we have a continuation of the algorithm right here. Now that we've finished running this, we go for k equals 1 to the length of n, and then we just set some things equal to 0, right? Can anyone guess what the time complexity of this would be? Yes?
Just n.
Exactly, that's just n, right? Because we're just looping through that vector one more time. So this block of code has one section that's O of n squared, and then it has another section that is O of n. So when we're talking about the time complexity of this entire function, or this entire block of code, what would that be? Yeah, O of n squared, right? We don't have to say O of n squared plus n, because as the length of our vector grows towards infinity, this part is going to get so much more expensive than this part. So we don't even need to care that that second part is in there. We only care about the time complexity of that top part, which is O of n squared. So a couple of things that you can sort of think about as you're trying to determine what the complexity of something is going to be. If you see nested for loops and they depend on the length of your input or the size of your input, each nested layer that you have is going to basically multiply that complexity by n, pretty much. So because we had 2 nested for loops, that was n squared. If we had another nested for loop in there, that would be n cubed, and so on, if it's depending on exactly the length of the input. When we talk about like splitting something in half, right? Splitting something in half multiple times, that should immediately tell you complexity of the order log n, or n log n. Something to do with logarithms, right? Because when you think of something that's, for example, 8 units long, how many times can you split that in half? You can split it in half once, that gets you to 4. Split it in half again, that gets you to 2. Split it in half again, that gets you to elements that are just 1. And then you can't split it anymore. How many times did we do that? 3, right? Because the log, base 2 of 8, is 3. So when we talk about splitting things, that's going to be logarithmic in complexity. So you'd have to take a look at these loops that you have right here, and if this loop was doing something that's splitting instead of just looping through each of the elements, then we'd go into more of a log n complexity instead of an n squared. Also, when we're talking about, say we have an algorithm that has to check every possible combination of something, when we talk about combinations and permutations, you may remember from mathematics what those formulas are. Those formulas tend to be, how many combinations of 5 elements into 3 spots can you have? That's all dependent on factorials, right? So those algorithms are going to be quite expensive because they are going to be of the order n factorial. So you always want to be thinking about these things because you may find, an amazing algorithm that solves a problem by checking every possibility and seeing which of them works. That's going to be factorial in time. That is not going to be a very good algorithm. It's going to get very expensive very quickly. This is just an example of how we would actually go through a piece of code and determine what the big O or the efficiency of that code is. And yeah, you see those n squared and n, and those just end up being O of n squared at the end. Now, a good way of thinking about big O and a good way of sort of understanding how big O works conceptually is to look at the process of sorting. Sorting is one of the most common problems that you'll have to solve when you're running an algorithm. Well, you're not going to have to do it because some very smart people in the past already came up with some amazing ways to sort that are very efficient. But it's a very good way of understanding how big O works. And I had printed out a couple of numbers over here and was going to have some people come up and actually sort themselves. We don't have too many people over here, so I'll just do it on the board. And we'll, what?
Get 5.
Yes. I don't think anybody wants to come up here and sort pieces of paper, so I'll just do it on the board.
It shows the video where they do it.
Yeah, that's a
funny video.
That is a funny, and it's a very there's these very satisfying videos of different sorting algorithms and placing things in order, and it's pretty satisfying. But those videos go through things very fast, so we're going to take it a little bit slower, just so that we can understand how these sorting algorithms work and what the efficiency is going to be for each of them. So the first sorting algorithm we're going to talk about is called bubble sort. And bubble sort, you'll see, is quite an inefficient sorting algorithm. Not the most inefficient, but it is quite inefficient. So I'm just going to create a vector over here, just some random numbers. Just that. So what bubble sort does is going to loop through this vector multiple times. And it starts at the front, and it tries to bubble the largest element of the vector all the way to the end. So that after each iteration of this sorting algorithm, the largest element, the next largest element of our vector, will get moved to the end to its correct position. The way we do that is we start at the front, we look at this element, and we compare it to the next one. If it's bigger than the next one, swap it. So is 8 bigger than 6? Yes. So we swap it. We know the first element is going to be 6. Now we're going to compare 8 with 9. Is 8 bigger than 9? No. So 8 stops right here. And now we're going to start comparing 9, right? Is 9 bigger than 7? It is. So we swap them. Got 7 right here. Is 9 bigger than 5? It is. So we keep pushing 9 forward. So 5 is going to stay there. Is 9 bigger than 3? It is. So we again keep pushing 9 forward. Is 9 bigger than 10? Not. So we stop. We leave 9 right there. And now we start looking at 10. Is 10 bigger than 2? Yes, it is. So there goes 2. And there goes 10. So after one iteration of bubble sort, our largest element, 10, has moved to its correct position. And we see that these other large elements, like 8 and 9, have moved closer to their correct position. Notice how 9 was over here at the start? Now it's almost at the end, right? So we've moved closer to the correct position. Now let's do this again. So is 6 bigger than 8? No, 6 stays in the same place. Is 8 bigger than 7? Yes. 7 goes back, and we keep moving 8 forward. Is 8 bigger than 5? Yes. Is 8 bigger than 3? Yes. Is 8 bigger than 9? No. So we leave 8 right there. Then now we start looking at 9. Is 9 bigger than 2? Yes. So we leave 2 right there. 9, 10. And there we go. Now our second largest element is in the correct spot. So we've moved 9 to the correct spot, and notice how we've moved 8 a lot closer to its correct spot as well. And we're just going to keep doing this, right? That 6 is going to stay there, 5, 3, 7, then 2, 8, 9, 10. The next iteration, we've got 8 in its correct position, and we can keep doing this for a while, right? We're just going to keep repeating this until eventually our vector is completely sorted. Let me see, what would the next step be? We would have a 5, 3, 6, 2, 7, 8, 9, 10, and then we'd have, it's just going to keep going, and eventually it's going to be sorted. This one was particularly out of order at the start, which is why it's taking so many steps to get it to actually be sorted at the end. So notice what this algorithm is doing in terms of how many times it has to loop through this vector. We loop through it once, and we move one element to the correct position. We loop through it twice, we move the second element to the correct position. We loop through it 3 times, and we move the third element to the correct position. So if this vector, let's see, how many elements does this have? 8 elements. On average, it's going to take us looping through it 8 times to get all of them in the correct location. So we have to loop through an 8-element long vector 8 times. That is 64 operations that we have to do. That tells us that the big O of this algorithm is what? N squared. Perfect. Because for an 8-element long vector, we have to do 64 operations. The bubble sort is an O of N squared algorithm because the amount of operations we have to do scales with the square of the input size. This algorithm is also iterative. I don't know if any of you were here for the other extra credit seminar that happened last week, the one on recursion. We're going to see some of these sorting algorithms are recursive. And it's okay if you don't understand what that means right now, but just know that bubble sort is an iterative algorithm. So now, let's go to the next one. I'm just going to use the same vector. The next algorithm we're going to be talking about is called Insertion Sort. And what Insertion Sort does is it, again, will loop through all of your elements, and it's going to take an element, it's going to look at everything that's before that element, and whatever is bigger gets moved after that element. So let's see how that looks like in practice. We start at the first element. Whatever is before, well, there's nothing before, so we can just skip it. We can just leave this right here. So we've stopped right here, and what's kind of nice about insertion sort is that everything then to the left of the like the iteration number that you're on is already going to be sorted. So 8 by itself, right, is just sorted, right, because it's just one number, right? Now, we go to the next one. We go to number 6. So we take everything that's to the left of 6, and if it's bigger than 6, we move it to the right. So we're going to get this. And then all the rest are going to stay the same. And we've stopped right here. Notice how everything to the left of this mark is sorted, right? 6, 8. That's in the right order. Now, we go to the next one. We look at 9. Everything that's bigger than 9, that it's to the left, we move to the right. Well, there's nothing bigger. So we just leave it like this. Boom. Everything to the left of this is sorted. 6, 8, 9. Then we look at the fourth element, 7. Everything that's bigger than 7 gets moved to the right of 7. So we're going to get 6, 7, 8, 9. And then there's the rest. There we go. Everything before this mark is sorted. And so on. We keep doing this, right? Now we're going to look at everything bigger than 5. And we're going to have 5, 6, 7, 8, 9, and then 3, 10, and 2. And everything to the left of this mark is sorted. So that's the idea behind insertion sort. Now, notice that for this algorithm, again, we are going to be looping through each of these elements, right? Because, well, actually, we're only going to be looping through the elements to the left of the one that we're looking at right now. But how many elements there are to the left of an element is going to be a function of how many there are in the vector itself. So it's almost equivalent to having to loop through the entire vector. And we have to do this, again, n times based on how many elements we have in our vector. So if we're looping through a vector n times and looking at n elements in that vector each time, once again, insertion sort, just like bubble sort, is going to be O of n squared. So this is also not a particularly efficient sorting algorithm because, once again, the time it takes to run it will scale with the square of the input size. We're going to have to do, again, 64 comparisons in order to actually run this algorithm. So insertion sort, it is also iterative, and it is O of n squared. Now these two are usually the sort of simpler algorithms, and they're usually what humans will do in their head. But these two, plus another one called selection sort, are the ones that humans typically do in our heads when we solve these problems, because we're usually not having to sort massive lists of like thousands of things by head, right? So for humans to sort a list like that using insertion sort or bubble sort, pretty easy, right? But when we actually have to sort through thousands and thousands of elements in a vector, or a librarian that might be having to organize their library that has thousands and thousands of books in alphabetical order, using one of the other sorting algorithms that we'll talk about now might be a little bit quicker. So the next one we will talk about is called merge sort. And I will use this same vector to display it. So the next one is merge sort. Now merge sort, you'll see, is going to be quite different from any of these other ones that we've just talked about, because it's not going to rely on, starting at the front and going all the way to the back of our vector many times. It's going to do some different kinds of operations. So merge sort is going to split our vector in two. So we're going to take the first half of our vector, and we're going to make it into like a sub-vector almost. And we're going to take the second half and make that into another sub-vector. Then we're going to take each of these sub-vectors and do the same thing. We're going to split them again. And we're going to get something like this, where we've got multiple vectors now that are pretty small. Now, if you want, at this point, you can split it again to just make each of them one element long. But this is already good enough, at least to display it. Now that we've got each of these subvectors that are 2 elements long, each of them, these are each very easy to sort, right? Just one operation we have to do, and they're sorted, right? These two, okay, they're not sorted, flip them. These two, flip them. These two, flip them. And these two, flip them. Now that we've got each of these small vectors sorted, we're going to start doing the merge of a merge sort, and we're going to start joining these small vectors together and placing them in order. So we're going to look at these and we're going to compare them to see how, what order they should go in. So when we merge these two, that's going to give us 6, 7, 8, 9. We're going to merge these two, and we're going to get 2, 3, 5, 10. And now, we're going to take these two vectors, each of them which are sorted, and we're going to merge them together again. And we're going to get 2, 3, 5, 6, 7, 8, 9, 10. And that's it. That's how merge sort does it. So it's still going to have to do at least n comparisons in order to basically do this actual merging procedure. Still going to have to do a bunch of these comparisons there, but it doesn't have to loop through each of these vectors like n times. It doesn't have to loop through this entire vector n times in order to do all of this. It just has to split this vector multiple times and then loop through these small vectors over here to sort them, which is a lot cheaper than having to loop through the whole thing. So merge sort, because it does these comparisons over here and it does this splitting many times. Remember when I was talking about what I was talking about earlier when it comes to these? How can we identify what the computational complexity of a certain algorithm is going to be based on what we see, like in the code, for example? If something gets split in half many times, what does that tell us about the complexity? Does anyone remember? Yes. Exactly. It's logarithmic, right? So that splitting is going to be a logarithmic procedure, and the actual comparisons are still going to be O of n, right? Because we still have to do at least n comparisons. So the big O for merge sort is going to be O of n log n. This n right here comes from the comparisons, and the log n comes from the splitting. So it's going to be O of n log n. And actually, n log n is better than n squared. N log n grows a lot slower than n squared does. The merge sort is a much better algorithm for sorting than insertion sort and double sort are. Now, another big difference about this algorithm and the other ones we talked about earlier is that this is a recursive algorithm. Now, recursion just means that a function calls itself. If you were at the extra credit seminar for that, you'll know all about it. But really what we're doing is we're calling merge sort on this big vector. And then that merge sort call splits the vector into two. And then we call merge sort again on each of these small vectors, right, which splits them into two. And then we can even call merge sort on each of these small vectors. That's going to split them. And eventually, everything's going to get merged back together. That's why it's recursive. Yes?
What if we have an odd number?
then we would, like, if we just didn't have one here, then this would just be a vector of 1, and that's even easier. We just, like, we don't even need to worry about sorting that one then.
How does it put it back together without inherently sorting?
It's going to merge these two together.
How?
It's going to compare this with 5 and with 3, and it's going to put them in order.
Isn't that adding more to the time?
Well, yes, but because we know that each of these smaller ones is already sorted, we don't have to compare the ones inside of these. We just have to compare them with the other ones. So we don't have to, so for example, when we do this, when we merge this with this, we don't need to worry about comparing these two. We just have to compare this, that, and that. And if there's an odd number, then this is just going to have one less for us to compare with. So it really, in the grand scheme of things, when something is 1,000,000 elements long versus 1,000,001, one extra comparison isn't going to make a big difference. But yeah, so really what we care about is when we take it to infinity, and that's why the efficiency is just going to be n log n, regardless of even or odd. Any more questions about merge sort? This is one that's a little bit counterintuitive at times. Cool. So finally, the last one we're going to be talking about is called quicksort. And as the name suggests, quicksort is going to be pretty speedy. It's going to be pretty much the best sorting algorithm that at least I will see today. There are a couple other ones that do some other funky stuff that can be faster at times. But in general, when we want to sort just any set of things that they, if we can sort, if we want to be able to sort integers or strings or numbers that aren't integers, then quicksort is going to be our most reliable companion. The way that, the way that quicksort works is it takes this vector that we have right here, and it defines something called a pivot. And everything that is bigger than the pivot goes to the right. Everything that's less than the pivot goes to the left. So in here, selecting the pivot is hard because ideally we want something that's right in the middle, right, to get as much as we can to the left and to the right. We don't know how to find that one, that element that's going to be the best pivot. So the more like naive way of doing it would just be select the first element, call that your pivot. So we're going to do that. We're going to make our first element the pivot. And now we basically take everything that's smaller than the pivot, move it to the left. Everything that's bigger, move it to the right. So we would have 6, 7, 5, 3, 2 over here, and 9 and 10 over here. So in this case, we have to preserve the order that they came in originally, because we can't just, I'm just going to move them over here and sort them already. Well, the computer can't do that, right? So it needs to pull them out in the order that they are in the original vector. And now what we do is we do the same thing with these two subvectors that we have. So we take this little vector right here, and we select the pivot in this. I'm just going to pick the first one again. So we keep this 8 over here. I select 9 as the pivot for this. Everything that's bigger than 9 goes to the left, goes to the right. Everything that's less than 9 goes to the left. We've only got one other number in there. So 10, right? That's done. Here, we need to pick a pivot again. I'm just going to pick 6. Everything that's bigger than 6 goes to the right. That's just 7. Everything that's less than 6 goes to the left. That's 5, 3, and 2. Now, all of these are each just one element long. We don't need to worry about splitting them or picking pivots with them anymore. This one is still 3 elements long, so we still need to pick a pivot for this. Based on the way I'm doing it, we'd have to pick 5. So everything bigger than 5 goes to the right. Everything less than 5 goes to the left. We'd have 3 and 2 in there, and then, all these other ones. And again, we'd have to pick a pivot over here. There's just 3 and 2. We pick 3. We're going to get that completely sorted. So this is basically the way that quicksort does it. It takes this vector, splits it in what ideally would be splitting it in half, right? Moving half the elements to the left of the pivot, half the elements to the right of the pivot, and just doing this process again and again until eventually we get subvectors that are just one element long, and they will all be sorted. Now, this algorithm, when it's done well, when it's done with a good pivot, is actually going to split that vector. Like if we have the perfect pivot for every operation, we have the exact middle element of that vector in every iteration, then it would split the vector exactly in half at each iteration. That should remind you of what merge sort was doing, splitting things in half. That's going to be logarithmic in time as well, right? So quick sort, when you've got good pivot selection, it's going to be n log n in terms of its complexity. If we have bad pivot selection, if we pick the largest element in the vector as the pivot every time, then we'd have the largest element and then everything that's less than that on the left. And then we pick the largest one again. We have everything that's less than that on the left again. You can see how it's going to be very similar to some of the other algorithms like bubble sort and insertion sort in that you're going to have to do that n times if you just pick the largest one every time. So in the worst case scenario, if you're just terribly unlucky in how you pick these pivots and you happen to pick the largest element every time, then quicksort is going to be O of n squared in complexity. That's why I've got this little asterisk over here for n log n. It's n log n on average. On average, you won't be that unlucky, and you won't get these terrible pivots. But if by chance you do, then in the worst case, it's going to be O of n squared. So that is the main idea behind quicksort. And this is actually what MATLAB uses to do sorting. So the sort function inside of MATLAB, well, that's, I think, pretty highly secretive what the actual sort function in MATLAB does, because it's quite efficient. And if these other programming languages get their hands on what MATLAB is doing, then they may want to implement that as well. But it's probably some variation of quicksort that MATLAB is doing in order to actually do the sorting. Maybe with something to account for the fact that, maybe you'll take a bad pivot and that's going to screw everything up. So it might throw in some merge sort or something else just to account for those cases. But on average, that's what MATLAB is doing. Any questions about any of these different sorting algorithms? Oh, also, quicksort is recursive as well because, again, it's doing that splitting and it almost has to call quicksort on each of these extra bits. Yes, Oliver.
So is there any reason to not use quick or merge sort because they just seem better, inherently?
They are better. Really, the only situation in which you might want to use, I don't think you'd ever want to use bubble sort or insertion sort. There are other situations where, for example, you know that your vector is going to be in a certain way, and you know that one of these algorithms might struggle with a vector that is that way. For example, quicksort over here, this algorithm, the way that we were doing it, we were picking the first element as the pivot. Think about if this vector was in reverse order, right? What if we had a vector like this? And we want to sort it in, but we don't know that it's like this, right? We want to sort it in ascending order. Well, if we pick the first element as the pivot, then the first time we're going to pick 5, the second time we're going to pick 4, the third time we're going to pick 3, and so on. We're always going to pick the worst element, right? So if we kind of have an idea of a bit of like what we expect our vector to look like, we can tell them, okay, maybe quicksort isn't the best for this because it's going to be O of n squared. So maybe use merge sort, something like that. Also, if you know, for example, that you're only going to have integers and you're not going to have decimals or anything else, there are some other sorting algorithms that can work quite well that are optimized to just deal with integers. Like Radix Sort, I believe, is one of them, and it is actually O of n in its complexity. So if you know that your problem is only dealing with integers, then you can throw in another algorithm that's better. But for just, we have no idea about what this problem is going to be at all, then you're probably best with quicksort or merge sort. Any more questions? All right. So now, let's talk about how this can be applied in the real world. And this talk about computational complexity is actually a very big part of computer science research right now, because perhaps the biggest unsolved problem in all of computer science right now, and even one of the biggest problems in mathematics, actually has to do with computational complexity. Because like I said, this has very big implications for anything out in the real world. You always want to have the most efficient algorithms that are going to solve the problem that you have, right? Or else you're going to be wasting time, you're going to be wasting resources, especially when you get to this massive scale that like tech companies are using, for example. So one of the biggest unsolved problems in computer science actually deals with this computational complexity and whether there are better algorithms to solve some problems than what we know right now. So in order to understand what this problem actually is, we have to understand different kinds of problems that we can have. One of this set of problems that is usually denoted P is going to be the set of all the problems that are solvable in polynomial time. What does polynomial time mean? That means that there's an algorithm that can solve them that is O of n to the something, right? And that doesn't include n to the n. We've already talked about that at the start and said that that's not a very efficient algorithm. But something that's in polynomial time can solve a problem on the order of O of n squared, or even O of n cubed, or O of n to the fifth. But it's O of n to a fixed number, right? And a lot of these problems we've been talking about, like the sorting problem, for example, are in this set of problems called P, right? As you can see right here, sorting can be solved in O of n squared time, or less, right? Quicksort is O of n log n. We can kind of also consider that polynomial time because n log n is better than n squared. So really, polynomial time is anything that's solvable as a function of n squared, n cubed, or better than that, like n log n, right? Sorting is that problem. We have algorithms that can sort in n squared time. String matching, that's what strcomp does in MATLAB. That's also a problem that's solvable in polynomial time, right? We just need to compare the two strings, right? If both of them are n units long, that's at most n squared comparisons we'll have to do. So string matching is also a problem that is solvable in polynomial time. Primality check. That's checking if a number is prime or not. That's also solvable in polynomial time. So each of these are problems that are pretty easy to solve in computational terms, right? Because we have algorithms that can solve them in these kinds of complexities. But now, let me give you a different problem. A problem that's not in computer science, but is a problem in interior design. So my parents are actually remodeling our bathroom back home, and they're trying to look for tiles to put on the floor of the bathroom, right? Make it look really nice. And so, of course, as a great child, I went and spoke to one of my friends in the School of Industrial Design, and I told her to design a couple of tiles to put on the floor of my parents' house. And she came up with these designs right here, which are absolutely beautiful. I mean, who wouldn't want to live in a house that has this for a bathroom floor, right? Now, I'm going to put some constraints, though, because, I'm not a maniac, so I'm not going to put this tile right beside this one with the green touching the orange like that. That's not going to look good. So the problem that I have is I'm given these different types of tiles. Each of them is like a foot by a foot, right? And I want to tile a bathroom floor that is n feet by n feet, so that I only get colors that touch each other beside that. So I couldn't put, for example, this tile right beside this one like that, because the green would be touching the orange. But I can put this one beside this one because it's pink touching pink. That works, right? And I want to be able to tile a square bathroom using just these tiles. And I can rotate them, I can move them around, but I've only got these ones. So really a more formal statement of that problem would be, given k different types of tiles, which are each 1 foot by 1 foot, I want to tile a bathroom that's n by n feet, so that only these matching colors touch. Now, I could tell you, hey, take a couple minutes, think about how you would solve this, see if you can think of an algorithm in polynomial time that can solve this problem, that can tile this bathroom floor, only as a function of, n, the number of feet that is the size of this bathroom. But I'm not going to waste your time on that, because if you can actually come up with that, you will be rich, because this is an extremely difficult problem to solve in polynomial time. This actually would be on the order of a factorial to solve, because the algorithms that we have for solving it right now would just have to look at every possible combination of these tiles on the floor, and eventually you'd get to one of them that works, right? You remember that combinations and permutations, as I was talking earlier, are always a function of factorials. So really the probability that you pick one that actually works is going to be something like 1 in n factorial or something like that, which means you would expect to get one that works after n factorial checks. So this is an extremely inefficient algorithm to solve this problem, and we really don't have a better polynomial time algorithm that can actually do this. But then I decided to take a trip to IKEA, and I rubbed a magic Swedish lamp that they had over there, and the genie of interior design came out, and he gave me this. It's a solution. It's a solution for a 4x4, but picture this genie can give us whatever solution we want, right? Notice how all the colors, they only touch the same color. So that's a solution for this problem that this genie was able to give me. And this genie can give me a solution for whatever, n by n, right? Can I check that this is actually a valid solution in polynomial time, right? So I can't find a solution in polynomial time. But once I have a solution, once this magical genie has given me a solution, can I check that it's a valid solution just in polynomial time? Well, what do we need to do to check that this is valid? All we need to do is we need to look at each of the squares and each of the 4 sides of it and see if it matches see if the color that's touching it matches that, right? So for this square, there'd be 4 comparisons we'd have to make. Or actually, we wouldn't even have to check these ones that are on the edges, right? But for this square, there would be 4 comparisons we have to make. For this square, there's 4 comparisons we have to make. So in total, how many comparisons do we actually have to make? Well, it's the total number of squares, which is going to be n times n, right? That's n squared. And it's times the number of edges that we have to check, which is 4. So we can check if this is a valid solution in just 4n squared, or really O of n squared operations, right? That means we have an algorithm to verify this solution in polynomial time. And the question that arises from this, then, is if we have an algorithm that can solve it, that can verify it in polynomial time, does that mean that there exists an algorithm that can actually solve it in polynomial time? So we can define a different set of problems right here called NP. There are the set of all problems whose solutions are verifiable in polynomial time. So if we have a solution, we can check if it's valid or not. And the big question right now is, does P equal NP? Are these the same thing? Just because we have a good way of checking, does it mean that we have a good way of solving it? And I gave you one very specific problem right here with the tiling of the floor. There are lots of other problems that are of this same type. Solving a Sudoku puzzle is the same thing. Solving the actual Sudoku puzzle is pretty hard computationally, but checking if the Sudoku puzzle checking if a solved puzzle is a valid solution or not, very easy, right? Just check all the rows, check all the columns, check all the squares. Pretty easy. But actually solving it, quite hard. Especially when you go from, that regular 9x9 Sudoku to a 16x16, 25x25, it gets very, very, very expensive to solve. So if there is an algorithm that can actually solve it in polynomial time, just like there is one to check it, then P equals NP. And that makes a lot of very, very, very difficult problems that we have nowadays extremely easy to solve. Because it just so happens that each of these problems, the Sudoku problem, the problem of tiling the bathroom floor, a lot of other problems can be reduced to almost like just a single problem. And if we can solve that one, then we can solve all of them. And this has massive implications, right? Because it allows us to just develop algorithms that are so much faster in solving many of the problems that we have nowadays. A lot of problems in biology, like protein folding, is a very expensive computational process. If we can find a faster algorithm for that, that could help speed up the discovery of the cure for cancer. So it's got lots of implications, and some of them are positive, and others are going to literally break all of society, because another problem that relies on the fact that it's very hard to solve is cryptography. Everything that like your bank uses to keep your password secure and to make sure that nobody can hack into your account, that relies on the fact that some problems are very hard to solve. So if we find an algorithm that's easy to solve them, then you're not going to have any more money in your bank account. But, you're not going to have any of the money that you had before, but if you do find the solution, you are going to have some more money in your bank account because of this. These are the Millennium Prize problems. They are a set of 7 problems that were, I think the Clay Math Institute set, I believe in the year 2000, that are the 7 biggest math problems for us to solve in like the next century or the next millennium. And one of them has actually been solved already. The Poincare conjecture has been solved. The other 6 are still unsolved. One of them, right here, is P versus NP. If you can solve this problem, you can make $1 million, because that's the prize for solving one of these problems. So you'll be out of the money in your bank account because you'll have broken cryptography and everybody would have stolen that, but you'd still get $1 million from solving this math problem. Now, if you've been thinking right now about that bathroom tiling problem that you have, and you've come up with a solution, please let me know, because then I'll submit it to this institute and I'll make $1 million. But if not, I definitely encourage you to think a little more about that and see if you can come up with something like that. It's very unlikely, but who knows? Maybe you'll have a spark of genius and you'll solve one of these big problems. So that's just a little bit more about the implications of computational complexity in the real world. What does that mean? Why is this even relevant? Well, that's because there are some pretty big unsolved problems in computational complexity that affect pretty much how our life is on a day-to-day basis. So I really hope that this was interesting, that you learned a little bit more about the problems that a computer scientist or just a coder will face as they go into the real world. And hopefully you'll use this in the future as you're coding, as you're maybe writing an answer for the final exam, and you're thinking, oh, can I use masking for this problem, or do I have to use a loop? And then you'll think, oh, but the computational complexity of using a for loop is so much more. This is going to be so much less efficient. And I think of using a mask, and it'll make it so much easier for the TAs to grade your problems. So yeah, those are just a couple of things that you can think about and just ponder in terms of computational complexity and code efficiency. That is all I had for today. If anyone has any questions, I can answer them. If not, thank you all for coming. Have a great Thanksgiving break. And yeah, think about that. Let's see if there's anyone on this Blue Jeans call. Oh, yes, we do have people. If anyone who's on the Blue Jeans call has any questions, you can let me know. I can stay a little bit longer to answer them. We do have a couple of minutes left.
That's how you make $1 million.
That is how you make $1 million, yes.
You just have to solve the Millennium math problem.
Exactly. And yeah, you don't just have to solve P versus NP. You can solve any of these, really. Except for this one, that one's been taken. But if you can solve any of these other ones, you still get $1 million. I'm really teaching you how to make $6 million. That's more than you get from most classes here at Tech.
Why haven't you solved it yet?
Just haven't had the time.
I've been giving these people a head start. I mean,
I wasn't born when these were made, so.
All right. Well, if we don't have any questions on the Blue Jeans call, then I will stop the recording, and we will call it a day. This will be posted as well, this recording, and there will be a Canvas quiz that's posted in just a couple of days, or actually it should be releasing pretty soon. It's going to be due in a couple of days. You can just fill it out. It's going to be very basic, very easy. A couple conceptual questions, a couple, look through the code and tell me what the big O of that is. One of them where you do one of those sorting algorithms that I was explaining. So take some time, do that. It's pretty easy. It'll get you some extra points. And yeah, that's all. Thanks, everyone.